Have you ever played a game of chance that, well, didn't feel so random after all? Today we're going to take a look at a simple little party puzzle about hats that actually uncovers a really surprising pattern hidden inside what looks like total chaos. We're going to start with a nice, neat arrangement and end up with one of the fundamental constants of the universe. Okay, let's dive right in with a classic puzzle. So you've got three guests leaving a party. Their hats are all jumbled up in a box, and they each grab one at random. The big question is, what are the chances that nobody gets their own hat back? Now, we're going to solve this, but to really get it, we need to start with a much more orderly version of the problem. So before we get to the chaos in the box, let's back up and look at a simpler question. Just forget the mix-up for a minute. Let's just figure out how many different ways there are to arrange things in the first place. Picture this, right? Our three friends walk in, and instead of that chaotic box, they see three nice empty hooks on the wall. They all decide to hang up their hats. The question is pretty simple. How many different ways can their three unique hats be arranged on these three hooks? Let's just walk through the logic here. For that very first hook, any of the three hats can go there, right? So we have three choices. Now, once that's done, there are only two hats left for the second hook. And for that last hook, well, there's only one hat left to hang. Pretty straightforward. So, to find the total number of unique arrangements, all we have to do is multiply those choices together. 3 times 2 times 1 gives us 6. So, there are exactly 6 possible ways to hang those three hats on the three hooks. Simple as that. And this process, this way of counting, has a name in mathematics. It's called a permutation. A permutation is really just any arrangement of objects where the order matters. And the shorthand for this calculation, that 3 times 2 times 1, is called 3 factorial, and it's written with an exclamation mark. So for any number n of objects, the number of permutations is just n factorial. Okay, so we've mastered the orderly world of hooks. Now, let's go back to the chaos of the box. We're about to add one simple little rule that changes everything. Nobody can get their own hat. So here's the crucial difference in what we're trying to do. The hook problem was all about counting every single possible arrangement. But the box problem, that's about counting only a very specific subset of those arrangements, the ones where nobody ends up with their own hat. We're basically filtering for a special condition. And this special no-match scenario also has a fantastic name in math. It's called a derangement. It's a type of permutation, but it comes with that strict rule that nothing can end up back in its original spot. Okay. So let's apply this idea to our puzzle. We already figured out there are 6 total ways to hand back the hats. That's our 3 factorial from earlier. Now all we have to do is figure out how many of those 6 possibilities are actual derangements, where guests A, B, and C all get someone else's hat. You know, if we just list them out, it's pretty easy to see with a small group like this. There are only 2 ways it can happen. In one case, the hats kind of rotate one way. A gets B's, B gets C's, and C gets A's. In the other case, they just rotate the other way. In every other combination, at least one person gets their own hat back. And just like that, we can solve our original puzzle. With 2 successful outcomes, meaning 2 derangements, out of a total of 6 possible permutations, the probability is simply 2 divided by 6, which, of course, simplifies to 1 in 3. Now, here's where this gets really interesting. What happens when we scale it up? Listing the outcomes for 3 guests was easy, but what if there were 10 guests, or 100? This is where these 2 problems really start to go in different directions. So this brings us to a really central question. For large numbers, why is counting every single permutation so simple, while counting just the derangements becomes so incredibly complex? Well, the answer really is in the logic. Counting all the permutations is easy. It always follows that simple factorial pattern of just multiplying n times n minus 1 and so on down the line. But derangements are a filtered subset. We have to actively find and then exclude any arrangement where there's a match. And as the number of hats gets bigger, the number of potential matches we have to check for and kick out just gets mind-bogglingly complex. Whoa. Okay, that looks intimidating, but stick with me. This is the actual formula for counting derangements. You absolutely do not need to understand it. The only reason we're showing it is to make a point. It's way more complicated than a simple factorial. But the real magic isn't in the formula itself, it's in the answer it gives us. And that brings us to what the source material calls a beautiful fact. It turns out that even though counting the exact number of derangements is a huge headache, the probability of a derangement happening does something incredible as the numbers get bigger and bigger. It actually settles down. It stabilizes right here. Whether you have 10 hats, 100 hats, or 1,000,000 hats, the probability that nobody gets their own hat back always hovers right around 37%. It gets incredibly close to this number, but never actually goes past it. Isn't that wild? And get this. This isn't just some random number. It's actually 1 divided by E, or Euler's number, a fundamental constant of the universe, just like pi. It shows up everywhere, in things like population growth, radioactive decay, and, incredibly, in a random hat mix-up at a party. So, let's just put it all together. What's the big takeaway from our 2 different hat problems? On one hand, you have permutations, basically any old arrangement, super easy to count with a simple factorial. On the other hand, you have derangements, a very special arrangement with no matches. And while it's harder to count exactly, its probability reveals this stunning, stable pattern, zeroing in on about 37% or 1 over E. And that kind of leaves us with a final thought. We started with a simple party game, and it led us straight to one of the fundamental constants of the entire universe. It just makes you wonder, if a totally random hat mix-up can hide such a predictable and beautiful pattern, where else in our world might we find these amazing, stable bits of math just hiding beneath the surface of chaos?